João Luis Rosa, who is one of the contributors to this code or to compute the shadows of compact objects. He has made very important contributions and applications. And so he's going to explain us all the details of how to improve the initial code presented yesterday. And well, Joris, you can start whenever you want. Thank you.
Thank you very much. I'm going to speak about three main things in this presentation. I think those are the most important things I can contribute to the workshop. The first one is to show you, let's say, a more user-friendly version of the code, and also how to, because yesterday and the day before we have learned about how to make shadows from axial observations, which, for example, for M87 is perfectly okay, because we know that M87 is more or less axially positioned to us as observers. But in general, it would be very nice to also be able to produce observations with inclination. And that's one of the things I'm going to show you how. And the second thing I'm going to show you how to do is to implement your own models, because until now we have only spoken about black holes and black hole solutions and different accretion disk models, but always in the background of a black hole spacetime. One thing that I think it's really important for us to do, and that's actually one of the most important things we can do now with all of the data that we have and all of the different models waiting to be tested. One of the things that we can do is to extend the code not only to black holes, but also to other alternative compact objects, and check how they compare with the black hole case. And finally, on the third part of this talk, I'm going to give you a specific example of a model that we tested. In this case is the Gravastar model, and I'm going to show you what kind of analysis we can do with this code, and what observables we can extract, and what conclusions we can take, and especially how these apply to this topic of research of finding alternative compact objects that are compatible with the experiment. So for the first part, as I said, let's look into this more user-friendly version of the code, because if you are like me, the first time I got access to the codes, I had basically two reactions. The first reaction was surprise. I was, wow, there is a lot of things that we can do with this code. I thought many or the majority of the codes that existed before, they were all programmed in C, C++, and more complicated languages of programming, or not necessarily more complicated, but languages I was not used to. And it was really surprising for me to see how in a simple Mathematica notebook, we can make analysis as complex, as deep as the codes that Gonzalo and Diego shared were doing. But on the other hand, I had a second reaction, and my reaction was, this is going to take a really long time until I understand what's happening, because there's so many things happening here. There's so many different calculations, so many different things to do and to analyze, all of these lists to produce and to save the data. It's going to take a long time for me to learn how to make this work, and afterwards to apply this to my own models. So one of my biggest efforts, even before starting to work with inclination, my main effort was to take this code and make it into something more user-friendly. Because after all, and this is true for, I don't know, for any software or for any tools that we use in our daily lives, and not only us, but every field of research and every field of engineering, they all use different tools. And I think when we are producing results and we are producing data, we are producing observables, I think at some point it's more important for us to learn how to use the tool and not exactly to understand what the tool is doing at the back end. So that was my first effort. I wanted to take this code, and if someone wants to take the code and use the code for their daily basis, for their work, this person is more interested in knowing how to use the code and not exactly what the code does on the back end. So that was my first effort. So in here, I am presenting this more user-friendly version of the code, where everything that you need to use to make all the calculations before that Gonzalo presented yesterday, instead of having to manually put your values and to make all the calculations, run all of the different sections of the code. All you have to do is to learn how to use functions that have already been predefined. So let's see how this works. So first of all, just as an example, this code works with the black hole metric. So in here, in the section for the metric, we just have a simple black hole. We have the Schwarzschild black hole. And if you want to change for a different black hole spacetime, you can just come here and change the metric to whatever you want. There is a mass here, but the mass, as Gonzalo said yesterday as well, everything is rescaled to the mass. So we can just set the mass equals to 1. And this is the metric for your spacetime. Now, if you want to produce the observable in the space-time or a given shadow, a given intensity profile, what you need to do also, besides choosing a metric, is also to choose what is the model that describes your accretion disk. And in here, in the second subsection, we have a few accretion disk models already introduced. So we have the general one. This is the one Diego presented on the first day. I'm going to zoom in a little. So this is the general one. This is the standard and bounds distribution that was proven to be a good approximation for the intensity profiles that you get from magneto-hydrodynamic simulations with these three free parameters. So sigma, mu, and gamma, who basically control the dilation, the translation of your profile, and the skewness of your profile as well. And just to make it ready for use, we have already implemented 4 different intensity profiles. If you want to introduce your own profile, it's really easy. You just take one line of code exactly as one of these 4. You just change the name for whatever you want, and you change the parameters of your accretion disk. So in this case, we have 4 different disks with 4 different combinations of parameters, but basically you can choose whatever parameters you want, and you can just create your own intensity profile to work as you wish. The 4 intensity profiles that you have already ready for use are the ones we call the I-COOP profile, the light ring profile, the event horizon profile, and the central profile, and they are basically motivated by different stuff. So I think Diego also mentioned this before. For the I-COOP profile, we are motivating this profile based on the fact that very compact objects have this orbit around them called the I-COOP, the innermost stable circular orbit. And this orbit at r equals 6m for black hole spacetimes, and for very compact objects, it happens at r equals 6m, but for different objects, it might happen at different radii. You just have to choose and change it here, the value of 6 for whatever fits your model. And this model is motivated by this orbit, because we know that this orbit separates the stable and the unstable time-like orbit. So if you have an accretion disk that's made of particles, massive particles, these particles should move into circular time-like geodesics, and you expect the disk to exist only in the region where these orbits are stable. So this is exactly what we see here. So this is a plot of the 4 intensity profiles, and the I-COOP profile, it peaks at around 6m. So your accretion disk exists for a radius larger than 6m, and the intensity increases as you are closer to the center because of the increase in the friction. And then below 6m, orbits are unstable, so the intensity profile should decay really quickly. Now, a second disk is the light ring intensity profile, and this is motivated by a similar thing. So we know that if there is a light ring, even though the orbits above the light ring are unstable, these orbits can still exist, and so one can also consider that the accretion disk extends all the way down to the light ring. Finally, if you want to model the accretion of matter, the infalling of matter to a black hole with a certain event horizon, for example, at radius r equals 2m, like is the case here, you can consider that the accretion disk extends all the way to the event horizon, and then it disappears. The intensity profile quickly decays to 0, because after that you are inside the event horizon. You don't care what light comes from there, because light cannot escape. And finally, one additional profile that is particularly interesting if you are working with extensions to the black hole model, so alternative compact objects, also known sometimes as black hole mimickers or exotic compact objects. Sometimes some of these objects do not have an event horizon. And if these objects do not have an event horizon, there's no reason to exclude the possibility that matter can infall into the center of these compact objects and radiate from there. And so you have an additional model called the center model, where we assume there is a peak of intensity at the center. So for example, if you have an accumulation of matter plus an accretion disk, you can, for example, consider a distribution, an intensity profile that is basically the central one plus the ISCO one, for example. But you basically can construct your own intensity profile based on the ones you already have here, or the ones you can create by yourself using the general expression. Now, let's say that you have finally selected your metric and you have selected your intensity profile. It's time to start making the integrations and creating the intensity profiles, the observed intensity profiles, I mean, and also to check what the object looks like. So what the shadow looks like in that setup, in that astrophysical setup. Now, the point is, if you remember from Gonzalo's talk yesterday, what we had to do was relatively straightforward, although it can be complicated to grasp all the details. So we had to integrate this equation, starting from some point close to the observer, which can be far away from the center. We integrate the geodesic equation inwards, and inwards means that we have this minus sign here. And then whenever this geodesic crosses the equatorial plane, we have a when event to mark the radius where that happens. And also, if eventually we can find the minimum distance between the photon and the center, we change the sign of the integration. So we get a plus sign. And from that point onwards, we are dealing with an outgoing geodesic. And again, every time the geodesic crosses the equatorial plane, we have the when event to mark where this happens. That's it. Now, let's say that you wanted to change some parameters in your integration. So you wanted to change, for example, the inclination of your observer, or the distance that your observer is, or for example, you want to change the impact parameter of your geodesic. This can be a little complicated if you are dealing with a code that has all of the details expressed like that. So what we have in this code is, here it is, a function. We have defined the function that takes the position of the observer, the impact parameter, and the inclination of the observer as inputs. And then the output of this function is to make our integration and create a solution for the trajectory of the photon. So instead of having to manually change the code, all you have to do is to take a function that is already defined and change the parameters according to what you want. Let me give you an example. So let's, for now, close this section here and go all the way down here to the examples. And let's consider here the example of the geodesic integrator. So we have the function. Remember, the first parameter is the distance to the observer. The second parameter is the impact parameter. And the third parameter is the inclination. And now let's say, okay, we want to make an integration for these values, and we want to see what it looks like. Okay, all it takes is 2 lines of code. Here it is. You want to change, for example, you want to change your impact parameter. Let's make an impact parameter that is smaller. So let's say r equals 6m. You run it again, and here it is. Just in 2 lines of code, we can produce the images for the geodesics that we want, and we can even go closer. Let's say, for example, r equals 4. We have a geodesic that falls immediately inside the event horizon. So this line in black here is the event horizon. The observer is somewhere here to the right of the image. And we can even test, for example, okay, we know that for Schwarzschild black holes, the critical impact parameter is 3 square root of 3m. So let's take, for example, some geodesic that has an impact parameter slightly larger than this. And we can see that it starts moving around several times. You can even make it closer and closer. It starts going around several times before it is finally deflected away. Or even the other way around. We can take, for example, a geodesic that has an impact parameter slightly smaller than the critical. We know that in this case, the geodesic is going to infall, but you can make it closer and closer to the critical, and we see that it moves more and more before finally infalling into the event horizon. And as you can see, with just 2 lines of code, we can produce, for the specific space-time that we have chosen before, we can produce all the geodesics that we want without having to change manually the code itself, where the functions, where the integrations are being done. So let's just put this back to 7m. There it is. We have a very nice geodesic. and we are ready to proceed. Now, what we want to do when we are making the images for the shadow, we are not interested in a single geodesic. As Gonzalo showed yesterday, we are interested in computing a congruence of geodesics with different impact parameters and checking where these geodesics intersect with the equatorial plane. So to do that, we can make an integration loop. And so let's look into this section here. So what this integration loop does is, again, instead of calculating everything again and making the integrations everything again, we have just defined the function for the geodesic integrator. So what we can do for our loop is simply to take that function we have just defined and inserting that function into our cycle. Here it is. So instead of making this piece of code the same as the piece of code before, we create a function and we reuse the function everywhere in the code where we want. So this is exactly the same thing that Gonzalo showed you yesterday. The difference is that we have, again, one function defined for the geodesic loop. This function creates these empty lists where we are going to save the figures, so the plots of the geodesics themselves, and these three lists where we are going to save the values of the impact parameter and the radius at which the geodesic intersects for the first time, the second time, or the third time the equatorial plane. So all of this function does is to create this list for a given initial impact parameter, and until it reaches a final impact parameter in n steps, this function makes the integration, runs the geodesic integrator we have just defined before, and it saves in a list all of the points where, or in three different lists, all of the points where the geodesic crosses the equatorial plane. Now, if you remember from yesterday when Gonzalo was making his presentation, Gonzalo mentioned as well that the place where the light ring is problematic because usually if the light ring, the light ring is really thin, and so when we are making a geodesic integration like this, it is not guaranteed that any of your geodesics is going to fall close enough to the critical impact parameter, so you might not be able to see the light ring in your image. So what was the solution then? Well, the solution was to run another geodesic loop exactly like this, but with impact parameters closer to the light ring, closer to the critical impact parameter. So what do? Precisely the same thing. So we created a second function, a critical geodesic loop, that instead of running between the impact parameters that you choose, it runs already between the impact parameters that are critical. So critical plus something, critical minus something, and we are creating data only in that specific region to guarantee that the final data includes also the light ring. So we create these two functions and they basically do exactly the same as before. So let's see how this works. Again, instead, let's go back here to the examples, to the geodesic loop. We open the geodesic loop, and here it is. So now we have an additional function that takes as parameters the position of the observer, the maximum impact parameter where you want to start making your integration, the final impact parameter where you want to stop making your integrations, the angle at which the observer is with respect to the equatorial plane, and the number of geodesics you want to create for this particular range of impact parameters. It's relatively easy. I've also included this line so you have this bar, this progress indicator to see how long it takes, and we can just make this run. And you can see it takes, I don't know, maybe a few seconds. You can track how long it is taking. And again, in just 2 lines of code, 1 line of code to run the geodesic loop, and the second line of code to produce the images. Remember, the figures are saved in this list called figures. In just 2 lines of code, you can create a geodesic congruence that suffices whatever needs you want. So for example, in this case, we have a geodesic integrator that goes from impact parameter equals 10 to impact parameter equals 0. you see, okay, there's a few geodesics here that might not be interesting because the impact parameter is too large. So we can, for example, reduce the impact parameter to a smaller value and check what happens. And for example, if you want to see what happens close to the light ring, you can take, for example, impact parameters closer to the light ring. So let's say +5 and same thing, but -0.05. So we are producing geodesics only close to the critical curve, so close to the critical impact parameter, and we can have a more precise grasp of what's happening closer to, or for geodesics that come with impact parameters closer to the critical one, and see what happens. Let's just wait a few seconds. And here we are. So for geodesics, there are some numerical points here that are falling a little away, but for geodesics closer to the critical impact parameter, we can see that these geodesics, some of them will fall inside the event horizon, some others will escape, but basically you have a grasp of what's happening here. So let me just put this back to 10 and this back to 0, and I'll let this run, and in the meantime, I'm going back to the functions. So we have created a function to integrate a single geodesic, and we have used that function to create a loop, and with this loop, we create a congruence of geodesics that we can see. Now, we are interested in producing a shadow based on this congruence of geodesics and based on a given model for the accretion disk, and for that, again, we have a function that does everything for us. So what this function does is exactly the same as the functions shown by Gonzalo yesterday. It takes a given range of impact parameters, makes the integrations, saves the list where the intersections of the geodesics with the equatorial plane are for the first, second, and third time. And now we have to start making the radiative transfer and producing the observables. So if you remember from yesterday, what was happening was that we would take the value at which the value of the impact parameter for a given geodesic, and as for the observable, we take the disk model for the particular radius at which this happens, and we multiply by the metric to take into account the gravitational redshift. We do this for the direct image, and then for the direct image, we have to choose the values between which the image is. We do the same for the secondary image or the lensed image, and we do the same for the light ring contribution. We, in the end, after everything is done, we interpolate all of the three functions to have a single function with the sum of the three intensities, and finally, we can normalize everything to the maximum intensity. So we have a plot with an intensity, a unitary intensity. After that, what do we do? Well, same thing as before. We produce a table with the data to make the intensity profile. And finally, we rotate, using the density plot, we rotate that intensity profile around the vertical axis to produce the observable, the image of the shadow in polar coordinates. And this is exactly what is done here. So we have the data for the intensity profile, and we have the data for the shadow. In the end, we just need to plot the shadow using the density plot, and we have everything that we need. Now, one advantage of doing this is that, let's say you want to produce, let's say you have one model, and this model has several different free parameters, and you want to produce data for different combinations of parameters, let's say. It's easier to do this if you have already a function defined, when you can just change the free parameters and run one line of code for each. And I'm going to show you how that is. And for every time you run this function automatically exports the data for the intensity, the data for the shadow, and the shadow plot as a PDF file. So this function takes as arguments the position of the observer, so the distance of the observer, the initial and the ending impact parameters where you want to produce your geodesics, the inclination, the number of steps between the two beginning and ending impact parameters. That's basically a different way to say the resolution or the radial resolution of your image. It takes the accretion disk, the intensity profile of the accretion disk also as an input, and it takes these three names here. This is just the names for your file. So you just, if you want to export the data, you just insert the name for the file where you take the intensity data, the name of the file where you take the shadow data, and the name of the file where you take the plot. So again, only one line of code that makes use of the two functions that we already defined before, and with this, we can produce an image. So let's see how this works. Again, back into the examples, take the axial image, and here it is. I've selected here a progress indicator as well, because this might take some time. To produce this, I'm not going to run this line of code because it takes, my computer is not very good. So it takes about 5 minutes to produce this image. So I'm not going to do that. Let's not waste time. But basically, this is what you get. So you have one line of code. This line of code takes all the data that you need. So all the parameters that you need, position of the observer, the range of impact parameters that you want to take. This is the inclination, for now, 0 inclination. This is the number of steps, so the radial resolution of your image. It takes a given function or the intensity profile of your accretion disk and the names of the files where you want to save the data to. You run this thing, after 5 minutes, you have your shadow image. Everything is all good. If you want to change anything, if you want to change your accretion disk model, if you want to change the position of your observer, or for example, in this case, you realize, okay, I started in an impact parameter that's 15, but I don't need 15, maybe 10 is enough because all of this region is black. You can just come here and change one parameter in the function, and with just one line of code, you get everything running for yourself. You want to change your accretion disk model. Okay, very easy. Just come here and change this input to something else. You can just come here. Okay, instead of the ISCO model, instead I want the light ring model, for example, or I want the event horizon model, or any other model. You can make your own model, as I showed you before, and you can just input the model here, and one line of code, you got your image. So let's put this back where it was, and this is what you get. Now, as I said, one of the things that we are also interested in, not only the image of the shadow, of course, but also the intensity profiles. The emitted intensity profile is the thing we have already showed you before. So we choose the intensity profile in the frame of reference of the accretion disk, but it's also interesting to see this same information that you have here, but for a radial intensity profile only. And if you remember correctly, this is the data. Let me show you again, just to make sure we are all in the same page. So there is a line of code here to export the data, and the data is precisely the data for the intensity profile of the accretion disk. So you choose this name, and this name, here it is. This is the file where the data for the intensity parameter is saved. So I'd say, okay, we have the shadow, but I also want to see exactly what the radial profile looks like. Okay, so let's go to the second example. Here we are, one line of code to import the data, one line of code to make the plot. And here it is, bam, bam, and we got the intensity profile of your black hole. If you want to change anything in here, that's pretty fine. Go back, change the data, change the parameters in the function, run the function, it saves your file, just rerun this plot, and you have everything that you need. You might realize that there are some little peaks here. This is just because I've chosen, to save some time, I've chosen a resolution of 100, but if you increase your resolution to 200, 500, whatever, depends on the time you have and also how strong your computer is. In my computer, I cannot go much further than 300, but you change your resolution, and this graphic becomes smoother and smoother. In here, it's not because, well, bad computer. But as you can see, just if you want to work with the code, and if you want to create your own intensity profiles, if you want to create your own black hole model or your own model, anything that you want to do is really easy. Your functions have already been predefined, and you can just take those functions, define those functions, take those functions, change the parameters, and you have everything that you need. Very easy. It's very straightforward to use the code, and not as complicated as it might have seemed if you were overwhelmed yesterday with the previous presentations. Now, let me go back to this geodesic integrator. Let me choose something that is slightly smaller. Let's say 5.5. Could that be enough? Okay, maybe even smaller. I'm gonna go almost to the critical impact. Okay, this is a good example. So, as I said at the start, for now, everything that we have done was to select a configuration where the equatorial plane is perpendicular to the line of sight of the observer. And when that happens, everything is very easy. You make one geodesic integration, you make one geodesic loop like the loop that is here. You compute the intensity profile based on the points at which these geodesics intersect the equatorial plane here, or for this one, for the third time as well. You make a calculation and you get the radial intensity profile. Now, if you are looking at the configuration face off, so your line of sight is perpendicular to the equatorial plane, all you have to do now is to take that radial intensity and rotate it along the axis of the observer to produce the shadow. Now, if you have inclination, this is not true anymore. You cannot do that anymore. So let me go back here. And let's take, for example, an inclination different from 0. It can be really small just for the effects. Oops. No, that's not that small, I guess. Okay, let me go back to another code because I think there's something here. Maybe I have to quit the kernel. Let me just try again with some different value just to see if it works, but I might have to change to a different notebook. Okay, maybe I'll have to quit the kernel. Something is not happening here. Let me just change to a different code and I'll show you exactly what happens when we are taking inclination. Give me just a second. And
on the mathematical.
Yeah. But I'm just changing the code because I have another one that might be here to show this. Okay.
Yes.
Okay, let me check if everything is working. Okay, perfect. So let me zoom in this one again. I'll check what's happening on the other one. Probably, I think it's probably just quitting the kernel, but I'll make sure before we give you the code. So what happens here? So let's say that I'm gonna again put this into a position closer to the critical impact parameter. Here we are. And now let's say for this particular geodesic with an inclination of 0, we have this line intersecting the equatorial plane at this point, and this point. Now, if I start increasing the inclination, what do I see? I see that eventually these points at which the geodesic intersects the plane, they start to change. So let's change it a little more. You see, these points start to change. And so we can say, for example, the equatorial plane is still in this vertical axis, but I'm going to make it a little more exaggerated now, but the observer is no longer on the left side of the image. The observer is somewhere here to the top of the image. Now, whereas if you have an axial observation, so perpendicular to the line of sight, it doesn't really matter if you shoot your geodesic. So let's say that this is the plane of the observer. It doesn't really matter if you shoot your geodesic from above that plane or below that plane, as long as the impact parameter is the same. The points at which the geodesic intersects the equatorial plane are the same. This is not the case anymore. So for example, let's say that the line of sight is somewhere here, so from the center of the image in the direction of the observer. You see, the equatorial plane is here vertically. If I shoot an image with this impact parameter, it will intersect the equatorial plane at some point. But if I do the same with an impact parameter negative, so to the other side, this geodesic will not intersect the equatorial plane at the same point as the first one. So this means that we can no longer rely on the intersection points for a given geodesic, for a given integration, to create all the other points around. We cannot simply make a rotation around the axis of the observer to obtain the intensity for all of the points around. So how do we cope with this? Let me go back to the other code again. How do we cope with this? Well, the thing is, we need to make some correction to the angle. So let me go back here. And let's now start dealing with the inclined observations. So the geodesic integration is basically the same. Your models, all of the models we are working with so far are spherically symmetric. And being spherically symmetric, this means that we can just make one integration. It doesn't really matter where around the object we make the integration. Everything is spherically symmetric. The integration is going to be always the same. What changes is for that specific geodesic integration, let's say we make an integration, if we change the position of the equatorial plane in this integration, although the geodesic congruence is the same, the points at which the geodesic congruence intersects the equatorial plane changes if the inclination of the equatorial plane changes. So what we can do is to produce exactly the same geodesic integration, exactly the same congruence. So the integration is, as you can see from here, exactly the same. This part of the function is exactly the same as we had before. You make the geodesic propagate inwards, and then you make the geodesic propagate outwards, precisely the same thing. But now we need to correct for the angle of the equatorial plane. So if you have the equatorial plane, let's say I'm the observer, this is vertical, and we have the equatorial plane here, and we have, for example, we are making an integration on this line, a vertical line in here. If I start inclining the plane, we have to make a correction on the angle at which these geodesics intersect the equatorial plane. And the same thing below. So if we are making the integration in this line right here, and we incline our equatorial plane, we have a negative correction because the equatorial plane is now closer to the observer than it was before. The only 2 points, or actually the only 2 lines, or the only line where you don't need to make any correction is the horizontal line. Because if you have your accretion disk here and you start making an inclination like this line here, so the diameter, the horizontal diameter of your accretion disk, the distance to the observer doesn't change. So the only place that doesn't need a correction is this horizontal line here. But every other direction around the axis that connects the center of the object to the observer, every other point needs a correction to make sure that the geodesics are intersecting on the plane in the right places. So to make that correction, there was a little algebra, a little mathematics behind the calculation here, but the correction, so the correction in the inclination is basically given by this line here. Arctangent of tangent of phi being the angle of the observer, cosine of theta being the angle of the equatorial plane. And basically, we have to add this correction to all of the geodesics that we have. So for example, if we are looking axially to the equatorial plane, so if our line of sight is perpendicular to the equatorial plane, this correction becomes 0, and you can come here and see that this basically becomes equal to the normal, to what we had before. So pi over 2 becomes, plus the correction becomes just pi over 2, and these are the points where the solution is intersecting the equatorial plane. Now, if your inclination is different from 0, then there is a non-zero correction, and you have to add this correction to the point at which there is the intersection. Now, we have an additional parameter in this function. This additional parameter is called the number of angles, and the number of angles is basically the number, or the resolution, the angular resolution of your image. So if you take, for example, an angular resolution of 1, the function will just make an integration like this and an integration like this. So one step. If you take a number of angles equals 2, the function will take 2 steps, so 3 different angles. it will integrate here, here, and here. If you increase even more the number of angles, you are increasing the number of integrations, not the number of integrations, number of corrections. The integration is always the same because, as I said, there's spherical symmetry, but you create the geodesic congruence and you have to correct for every or for as many angles as you want. The more, the better the resolution of the image if you increase these angles, but this also comes with the downside that computations take longer. So if you want to make a better image, you have to increase your your resolution, but you also have to take into consideration the limitations of your computer. For me, in my computer, if I increase too much the resolution, the angular resolution and the radial resolution, this can take a lot of time. The example I'm going to show you soon, it takes about half an hour to make. So we take all of these corrections from 0 to 180 degrees, so from 0 to pi. The corrections on the other side are exactly the same because, okay, this is inclined, but left and right, they still have the same properties. There's still a symmetry from left to right. So we make the corrections on these angles and we produce the lists containing not only the place at which the intersection occurs, but also at what angle this intersection is being computed. In the end, everything goes exactly in the same way. So first step, create the integration and create the corrections for all the angles, and then it goes precisely as it goes for the non-inclined case. So you take the geodesic integration, you loop for different values of the radius. So here they are, same thing as before, and finally you produce the shadow. Let me just close this as well. You produce the shadow in the same way. There is again only one additional parameter, the additional parameter being the number of angles, or in other words, the angular resolution of your shadow. So this is exactly what this extra parameter here is doing, but everything else is precisely the same. So the function goes again in the same way as before, precisely the same method. The only difference, and that's why it takes much longer to do this, is that this function, which before only had to do the analysis of the intensity for a single point and then rotate it around the center, now this function needs to do that analysis for every angle that you choose in your resolution. So instead of having a single point, a single line of code doing each of the calculations, we have to do a loop that goes through all of the angles that you have selected in your angular resolution. So it takes longer, but the method is exactly the same. And the function is longer as well because we have to do this. We have to add, instead of for each line of code, we have to add a loop to make that calculation for every angle. So a function is a little longer, but the idea is exactly the same. In the same, we export the data for the intensity and for the shadow, and we also export the shadow as a plot itself. So let's see what this looks like when we want to finally make this work. Let's go back here to the examples, and here we are. Give it a second. My computer is so slow that just opening this thing takes a few seconds. Here it is. So same thing as before. I've added the progress indicator so you can track how long this is taking, and one line of code with one additional parameter that is, this parameter was there already, sorry, this is the inclination, but one additional parameter here, which is the angular resolution. So this image was produced with 100 radial points and 100 angles between 0 and pi. So it makes the same calculation as before, but 100 times. And this is what you see. So this is for the I-COOP model, a black hole, and you produce the shadow. Maybe I can zoom in a little so we can see better what's happening here. Just takes a while. I need a new computer. Okay. It's frozen a little. Give it a second. He's doing his best. Okay. Here we are. So let's try to make this bigger. Give it another second. Okay. Hopefully only 10 more seconds. Okay, here it is. So you can see that the resolution is not very good because, as I said, there's only 100 radial steps and 100 angular steps. but you can see everything that you were expecting. So you can see the primary image. Here it is. It's not circular anymore. Now we have the trajectory of the particles in the accretion disk in front. They are not very deflected, but the parts of the accretion disk that are behind the black hole, they are extremely deflected. We also see the secondary image right here. So this part that you can see here is the secondary image. So the photons that are coming below the object. And finally, very thin, but actually still observable with this resolution, we have the light train, which you can see here and here. So everything works out. Everything is exactly what we expected. And we can also, with just a couple of lines of code, we can also produce the inclined observations. So this was first part of the talk. If you were super overwhelmed with the amount of code that you had on the presentation yesterday, fear not, we can do this with just a few lines of code by defining our own functions. And from these functions, it's very easy to just implement your own models and run your own code. Now, about implementing your own models. I've told you that it's very easy to implement your own model for the accretion disk here. You just have to change or to create an additional line of code here for a specific combination of parameters for the model that you want, and then you can just insert that into the produce shadow function. And if you just want to use a different metric for a black hole, for example, you can just add it here. Now the problem, or one of the problems, arises when we are interested in models that are slightly more complicated than just a black hole spacetime. So for example, let's say that you want to work with a model that has additional free parameters. So for example, even if you want to work, for example, with the Reissner-Nordstrom solution, not only we have the mass, but we also have the charge, and the charge changes the spacetime itself. And in here, in these functions that I've showed you, there is no way to change the charge of the black hole. So how do we do? How do we extend the functions that we have for additional metrics with additional free parameters? Well, it might sound complicated, but actually it's really simple. You just come here, line, let's say it's a Reissner-Nordstrom solution, and you want to add a charge. And you just give the value of the charge equals to the value of whatever. Here it is. So let's say you want to add an additional parameter to your model. All you have to do is simply to add these parameters here to the function. The more parameters that you are, the more parameters you have to add here. You just have to be careful, because now you have changed how this function is called, right? So I'm just gonna take this out so I don't forget. But let's say that we have had an additional parameter here, let's say for the charge of the black hole. This affects all the other functions. So we have to be really careful, and we have to go section by section here on the integration loop. We have to add this same parameter precisely in the same place for every function. And we must not forget to also add this parameter whatever the function is being called. So we would have to do it here. We would have to do it also in the critical loop here and here. And also we would have to do it in the shadow producer. So here and here, because this is basically the geodesic loops, the ones before, we would have to add the additional parameters. So let's say we could add it, let's say here, for example, and oops, and you would have to add it as well here and here. And that's it. So if you have a metric that is like a black hole metric, so it's valid for the entire spacetime, and you want to also use different values of the free parameters of the function, it's really easy. You just have to add them there, and you're done. You're basically done. You just need to rerun the function. So you would come here, for example, let's go to the examples for the axial, not this one, for the axial image. Here it is. You have this line of code to produce the images. How can you, let's say, how could you test what happens to a given free parameter? Very easy. You just go here, you make like 3 lines of codes, and you add different values of your free parameter. And with this 3 lines of code, you produce 3 shadows, each with different values of your free parameter. That's pretty much it that there is if you want to include a new metric on your codes that has additional free parameters, but that it's valid for the entire spacetime. Now, the problem arises, and that's the point where I'm going to change for the other notebook. The problem arises when you are interested, for example, in alternative compact objects, exotic compact objects, for which the metric is not valid for the entire spacetime, but rather you have 2 or more different regions. So I'm going to close this part as well. And take, for example, a fluid star or a boson star, stars like that. We know that these stars are made of 2 regions. You have the exterior region, and the exterior region is basically the Schwarzschild spacetime. And then you have the interior region, which changes from object to object. So the metric that describes your spacetime cannot be given in a single matrix. You have the matrix that describes the interior, and you have the metric that describes the exterior. So when this happens, how do we adapt the code for that? So this is the second version of the code I'm going to show you. If you go to the Wolfram community website and you search for our names and for our works, this is the version of the code that you will find. So this is the code that we have used for our work on gravastars. And all of the things that you need if you want to if you download the code from there, this is the code that you have. And if all of the things that you need to implement your own models when your space-time is divided into different subregions, everything that you need is here. So in the same way, you already have the accretion disks here, the accretion disks model, so the same models as before. This is just a copy paste from the other code. Here in the section geometrical quantities, you have not only the metrics, so you have this is the exterior metric, which, as you can see, is basically Schwarzschild spacetime. But then you have an interior metric. So the interior of this compact object is no longer Schwarzschild. There's some different metric that describes the spacetime, and you can add this metric here for the interior. I have also included additional lines that are not used in the code, but just in case that you need to make some additional analysis. So for example, let's say you want to check what the Christoffel symbols look like, or the Riemann tensor, the Ricci tensor, blah, blah, blah. If you want to confirm that everything is correct, you have here these additional lines of code with the geometrical quantities that might be interesting for what you are doing, but don't worry about that. These are only used by yourself if you want to test something. The only lines of code that are used in what follows are these. So you need to define the interior metric and the exterior metric separately. And then there is one additional section here called the composed metric, where we make the metric for the entire spacetime that we call G total as a piecewise function. So GTT, the TT component of the metric, is a piecewise function that takes the interior metric if the radius is smaller than the radius of the object, and takes the exterior metric if the radius is larger than the radius of the object. Let me zoom in a little. I think it's better. Same thing for the R component of the metric, piecewise, that takes the interior one if the radius is smaller than the radius of the object, and takes the exterior one if the radius is larger than the radius of the object. And since the spacetime is spherically symmetric, GTT and G5, we don't really care. They are the same for the Schwarzschild spacetime or for the interior spacetimes. Let me show you what this looks like for the gravastar solution, for example, just so you have, I made some plots here just so you have a grasp of what's happening. So if you choose, for example, a gravastar with a radius of 3, 4, or 5, what is happening here? So if the radius is larger than the radius of your object, so this is the GTT component of the metric as a function of the radius. If you have, for example, a gravastar with a radius r equals 3m, what do we see? Well, the radius of the gravastar is here. If you are outside of the radius of the gravastar, this thing, this function, just follows perfectly the Schwarzschild spacetime. But if you are in the interior of this exotic compact object, the metric changes. This is no longer Schwarzschild, this is something else. And it varies with the radius of your star. And in the case for gravastars, we have an additional free parameter. Not only you can control the radius of your object, but there's also an additional free parameter. And in many, if you are interested in exotic compact objects and doing this for alternatives to the black hole hypothesis, you will find that not only you can control the radius of your object, but there's usually additional free parameters to control. So for example, in fluid stars, you can control the mass on the shell. Same thing here, there is a free parameter that controls what portion of the mass of the gravastar is on the shell and what portion is in volume. And again, changing these parameters changes the metric. So again, we have GTT outside of the radius of the star, independently of the value of that parameter. You follow the Schwarzschild solution, but if you are in the interior region, then the metric changes depending on your parameters. So you have one spacetime that is defined not only by an interior and an exterior metric, but also the interior metric where your spacetime is defined, where your actual compact object is defined. Free parameters, in this case, 2 free parameters, control what is the shape of your metric. And that's something that makes this much more complicated. As for the metric, this is all you need. You introduce in this section the interior and the exterior metric. In this section, you combine the two with piecewise functions, and then after this, everything is exactly the same as we have seen before. So take, for example, the geodesic integrator. There's 2 lines of code here to compute the metric every time the geodesic integrator is going to run. And then not only we have as parameters for the function, the position of the observer, the impact parameter of the geodesic, and the inclination of your observation, but as I showed you before, the additional free parameters of the model go here. So in this case, we have this parameter alpha that controls the ratio of mass between volume and surface, and we have R that controls the radius of the gravastar. So at which radius you separate the interior solution from the Schwarzschild solution. And everything else is exactly the same. So we can just scroll down. We have integration, we have outer integration, same thing. In the geodesic loop, again, exactly the same thing. These functions are exactly the same as before. The only difference is that we have the additional free parameters here, which are given the values here and here as well, precisely the same, and also for the shadow producer. Now, there is one slight difference in the shadow producer, that is if it is necessary or not to compute extra data, additional data for the light ring. So remember the problem that we had when we were doing this for black holes. We know black holes have a light ring. The resolution of your image might not be good enough for you to see the light ring, and so you needed to create additional data in the impact parameter close to the critical impact parameter to make sure that you see the light ring. Same thing in here, but one interesting feature about exotic compact objects is that they don't always have light rings. They only have light rings if they are compact enough. And in the case of the gravastar, they only have light rings if the radius of the gravastar is smaller than r equals 3m, which is the radius at which the Schwarzschild solution has a critical curve. So in here, remember before in the code that I showed you before, you had these 2 lines like that, and you didn't have this because you know that the light ring is always there, so you always need to create additional data for the critical impact parameter. In this case, you know that you only have a light ring if the radius of the star is smaller than 3. So instead of having these 2 lines together, you only run the second integration loop if there is a light ring. This is the only additional thing. Everything else is the same. Again, in the parameters of the function, here we are. Everything is exactly the same as before, except that we have 2 additional free parameters here, the ratio of masses and the radius of the star. Everything else, as you can see, is exactly the same. It exports the data precisely in the same way, everything is exactly the same. So we have some examples here as well. We have the shadow for, in this case, for the central model, so the model that peaks at the center, for a specific value of the parameter alpha, that is the one that makes the star, the mass of the star, more at the surface and less in the volume, and the radius of the star very close to the Schwarzschild radius, and boom, what do we see? First interesting solution, first interesting result. I'm going to zoom in a little here. We see, and this is one of the things that I wanted to call your attention for, remember that this disk model is the disk model that peaks at the center. Let's go back here just so you believe me. So in C is the central disk model. It's the disk model whose intensity peaks at the center. And yet, if we produce an observation of this accretion disk, we do see a shadow. So even though this compact object does not have an event horizon, even though we are assuming that there is radiation coming from the center of this compact object, you observe a shadow. And this is one of the most important results that we have found so far in our research. You don't need an event horizon to create a shadow. You just need the effects of the gravitational redshift to be strong enough for you to not observe the radiation that's coming from the interior. The inclined shadow, similar thing. In this case, you don't see. Let's give it a second. If it is, in this case, you see this this little thing in the center because it's a different combination of parameters. In here, it's 1, 1, and 3. If you selected, for example, if you selected the values of the parameters same as before, you would also see a shadow. I'll show you that in a second. But basically, what I wanted to show is that it goes precisely in the same way. One line of code, you introduce all your data, all your parameters, you choose your accretion disk, you choose the files where you want to save, and in one line of code, this one takes about, I don't know, almost an hour. But again, my computer is not the best example. You should try it in yours, especially if you have access to a good computer, to a tabletop. It's probably going to be much faster. In my computer, not so much. But these images or inclined images take about 1.5 hours to produce. But note that the metric is much more complicated than a black hole, and it has additional parameters. So it's not that surprising. It takes longer. It's just what it is. There's not much to say about it. And as I said before, if you wanted to try combinations of parameters, you can do that just with single lines of code. Each line of code, each of these lines of code produces a shadow for a different combinations of parameters. You can just let this run, go to sleep. In the morning, you have all of your data ready, and then you can use the fact that all of these lines of code produce the data or create the data into a file. You can then import this data with the names that you have chosen before, and you can produce the intensity plots based on the data that you produced during the night. So all of this is really straightforward. You just need some practice to run the code a few times, see how it works. But I think it's really straightforward in the way that it is now. So one last thing that I wanted to show you, and I promise this is going to be fast. We are almost over. One thing that I wanted to show you is the kind of research that we can do with the code. So I prepared a really short presentation about this Gravastar solution and all of the results that we obtained using this code. I already motivated a little the use of exotic compact objects. In particular, we know that there is stuff in the universe. We observe this stuff that indicate that something very, very compact that kind of behaves like black holes exists in the universe. We have observations from the orbits of stars close to the galactic center. We also have the shadow, and we have the orbits of flares around the galactic center. All of these are very consistent with what you expect from the black hole spacetime, but black hole spacetimes have their own problems, because black hole spacetimes have event horizons, have singularities, Regular ones don't have singularities, but they have the problem of not having a natural formation mechanism. They are associated with the information loss paradox. So although the black hole spacetime is good in explaining all of these observations, there are some drawbacks, fundamentally mathematical and physical drawbacks, that it would be really nice to avoid. And so it would be nice to develop some alternative solution for a compact object that is able to reproduce the same observations without having these kind of problems with unphysical or mathematically complicated stuff to understand, like singularities and eventualities. So one of the models, several models have been developed: boson stars, fluid stars. In this case, I'm going to speak about gravastars because this is the code that is publicly available. Is a code that deals with gravastars. That's why I'm choosing gravastars to make this quick presentation. As I told you before, gravastars are solutions for for general relativity with an exterior Schwarzschild solution and an interior solution where there is some kind of fluid. This fluid is basically dark energy. So we can consider that the interior of a gravastar is basically dark energy. It's the Sitter space-time inside. And the metrics, I've already shown you how the metric looks like. These are all things made with the code. If you are in the exterior, the solution is Schwarzschild. If you are in the interior, the solution changes depending on the values of your parameters. And most interesting, and that's exactly why the code is important, is that depending on the values of your parameters, the directions or the trajectories of your photons, of your geodesics change. So here's just an example. So remember this parameter alpha controls the mass distribution. If alpha is equal to 1, the mass distribution is all in volume. If alpha is smaller than 1, down to a certain minimum value, the mass is transferred from the volume to the surface. And when alpha is precisely equal to that minimum value, all the mass of the gravastar is allocated at the surface. And if you change this, if you change the amount of mass that you have in volume and at the surface, you see that the trajectories, even though all of these geodesics came in the same impact parameter with the same direction, when they intersect and when they propagate inside the gravastar, you have differences depending on your model. So different models, we have different observational properties. And so when we consider accretion disks, we take, for example, just two accretion disks, the ISCO model and the central model, because we know that these models have ISCO, so have at r equals 6 the innermost stable circular orbit, and they don't have event horizon, so the central model is also an interesting one. We produce the observables, and we see that if we change, so in here I'm showing different combinations. So in here, these two plots are when the mass is completely distributed in volume. These plots is when the mass is completely distributed at the surface, and these models are for a radius of 2.01, so a very compact boson gravastar. What happens if we allocate the mass in different places? And you can see that both parameters influence the results. So for example, let's take the ISCO model, and let's take a gravastar that is very compact, and let's change the mass distribution of the gravastar from volume to surface. And you see that the different contributions in the image, so you have the direct image, you have the light rings, and you have the secondary, these contributions change from place to place when you change the values of the mass distribution. And the same thing here, if you consider a fixed mass distribution and you change the radius of the gravastar, the contributions also change in the ISCO model. And more interestingly, for the central model, which remember is the one for which the intensity peaks at the center, you can change the mass distribution of the gravastar, and you can have completely different results. This is for the intensity the intensity profiles, but let's see exactly what happens in the shadows. So this is for 4 different values of the radius. So 2.01, the most compact one, 2.5, 3, which is in the limit of ultracompacticity. Ultracompacticity means that there is or there is not a light ring. So the radius at which the light ring appears, it's the radius that separates ultracompacticity from non-ultracompacticity. So this is R equals 3m in this case, and R equals 4n is no longer ultracompact. And so what do we see? Well, for the I-COOP model, there are additional contributions because there's no event horizon, and we can see them for every case except for the non-ultra compact. And then it doesn't happen for the non-ultra compact because the light deflection is not strong enough to produce these kind of imprints when you are observing axially. But for the central model, a very interesting thing happens. If you consider a gravastar for which the mass is all distributed in volume, it doesn't matter what the radius of the gravastar is, you never see a shadow. But if you start allocating more and more mass at the surface of the gravastar, you see that eventually you can develop a shadow for the most compact models, or more precisely for the ultra compact models. And if you take now inclination into consideration, this is the same thing. In here we are changing the value of alpha, so we are changing the amount of mass that is allocated in volume and at the surface. For the I-COOP model from the central model. For the I-COOP model, as we can see, there are different distributions of images, different imprints for the additional images that you have due to the absence of the event horizon in comparison to the black hole spacetime as well. And for the central model, if you allocate the majority of the mass at the surface, at the beginning, when the mass is in volume, you don't see the shadow. But if you start moving more and more mass to the exterior, to the surface, eventually you see a shadow. And if you compare this with results from other spacetimes, this is what you see for a black hole spacetime, a clear shadow. This is what you see for a fluid star, a not so dark shadow, but it's still there. And it's slightly smaller than for the black hole case due to the absence of the event horizon. For a boson star, same thing. It's slightly smaller even than the fluid star, but it's darker. And this is what you see for the gravastar. So again, a very dark shadow with more or less the same size as the boson star. So fluid stars, boson stars, and gravastars, none of these models have event horizons, but they all produce shadows due to the effects of gravitational redshift. And this is one of the most important results that we have found thanks to this amazing code that we have developed, or more that Gonzalo and Diego have developed, and I just made a few things. Now, to conclude my presentation, how much time do I have? Like 10 minutes? 15 minutes, great. So almost done. I'll be done in 5 minutes. So conclusion. The most important thing I think to get from this, and this is basically my motivation in working with this code and helping to improve the code, and the objective of my research is to test the black hole hypothesis. Because as I said, black holes are really simple models and they explain pretty well the observations that we have, but there are several drawbacks that many people don't like. I particularly don't like the fact that there are singularities, for example, and so I would like to see a development of alternative models that can explain the same observations. And now that we have observations from the strong gravity regime with the Event Horizon Telescope and with the Gravity Plus experiment, now that we have all of this data, we have everything that we need, all of the astrometric observations that we need to finally put the black hole hypothesis to test and assess the validity of these alternative compact objects. And one of the things that we find, and that I showed you before already in this presentation, is that the more compact the object is, the more it resembles the black hole spacetime. So if you can develop a model for a fluid star, for a gravastar, for a boson star that is compact enough, chances are that they are very similar to, they have observational imprints very similar to those of black holes, with additional contributions. So for example, all of these models that don't have event horizons, they have additional contributions in the image. These are what we call the plunge through images. So photons that, if it was a black hole, these photons would fall inside the event horizon. But in this case, since there's no event horizon, there's photons that can cross the interior of the object, producing additional contributions. And because of that, you can also have slightly smaller shadows, but the shadows still exist, and so they can still be used to assess the validity of the models. If you don't have a light ring, also if your model is more dilute, In principle, it will not produce a shadow because the effects of gravitational redshift are not strong enough if you assume that there is radiation coming from the center. But if you assume an accretion disk at the ISCO, like we usually do, we can still produce observables that are similar to black holes. And in this case, inclination is one of the things that more strongly affect the results. So one can also use the observations with different inclinations. So for example, M87 is at an inclination, I think, of 17 degrees, more or less. The Sagittarius A star, the inclination is slightly bigger. So we could, for example, with better observations from these two sources, we could use inclination to test the validity of these models as well. And finally, the most important result, I can never say this enough, we can produce shadows even in the absence of an event horizon, as long as the effects of gravitational redshift are strong enough. And for these effects to be strong enough, you need your object to be very, very compact. So you need your object to have a light ring, to be compact enough to develop a light ring. And you need, in the case of a gravastar, this is not true for the other models, but for the gravastar, we need the mass distribution to be more at the surface and less in volume. This guarantees that the effects of gravitational redshift coming from the center, where we assume that there is emission, will be stronger, and so you can produce a shadow. So thank you very much. I am finishing a little early, but I hope we have some time for questions as well. I hope you enjoyed, and remember that the codes that we have used, they are available on especially the Gravastar code, so the more complete one that you can afterwards adapt for whatever needs you have. They are all available at the Wolfram community website, so you can download it directly from there. Or if you can't find it, also feel free to send us an email, and we very happily will share the code with you. Thank you very much.
Thank you so much, Alvis, for your very informative and nice talk. So I think there are a few questions. Marek, you wanted to ask something before?
Oh, yeah. Yesterday, Diego also mentioned it, and this thing of shadows being formed even in the absence of event horizons. Is it something that has been also observationally confirmed, or is it a prediction that needs to be observed observationally?
No, none of this has been visually confirmed because we have no confirmation of what the objects are. So we have confirmation that the shadow exists visually, but everything else is just theory and predictions until we have a clear indication of what the object that is producing a shadow is, which can be a black hole or can be any of these alternative models. Until we have a confirmation, all of them are equally acceptable, but this, for now, this is a theoretical prediction. We don't have a gravastar in your lab that we can just look at and say, okay, there's a shadow.
Okay, very good, thank you. Any other question, maybe online? Yes. You can read the question if you want, Joris.
Yes. So correct me if I'm wrong, that the existence of shadows in gravastars is due to the mass on the surface of a star. Yes. Is that what you said, or do you mean gravitational redshift due to no? So it is the caused by. Okay, let me rephrase. Maybe it's not that is the mass at the surface that causes the shadow. It's when the mass is allocated at the surface, the effects of gravitational redshift are stronger at the center, and that causes the shadow. So let me go back here. I can show you this with this. So notice in particular, which plot do I want? I want this plot. So can you see my mouse?
Yes.
Okay, perfect. So if you look at this plot, for example, so the effects of gravitational redshift, they basically depend on the difference between the value of GTT at the reference frame of the observer and at the reference frame of the emitter. So if you have all of your mass allocated at the surface, allocated in volume, this is alpha equals to 1. And when the observer is really far from the center, if the spacetime is asymptotically flat, which it is, then the value of the metric, the value of the GTT at the observer really far and at the center where radiation is being emitted is basically the same. So there is no effect of gravitational redshift. But if you start moving the mass of your gravastar to the surface, so basically if you start decreasing the value of alpha, you see that GTT at the center starts decreasing. And so the difference between GTT at the center and GTT at the observer are bigger, and that causes the effects of gravitational redshift to produce a shadow. So it's not the mass itself, it's the shape of the GTT that causes this, this effect. But notice that this is only valid for gravastars, because gravastars have a de Sitter interior, and it is the fact that there is dark energy that causes the GTT to increase back to 1 at the center. Because if you have fluid stars or boson stars, this doesn't happen. So in fluid stars and boson stars, the shape of the GTT is always something that follows Schwarzschild, like that, and then it goes like this, and it achieves some value, some constant value here, but this value is always smaller than the value at the radius. So in fluid stars and gravastars, as long as you have something that's compact enough, the distribution of mass doesn't matter, you always see a shadow. For gravastars, you need this additional thing that is to push the mass to the surface. You also have final question 2. Do the existence of shadows requires the existence of thin shells, double layers, etc. at the gravastar radius? So it requires the existence of a thin shell, that's for sure, because without the thin shell, you don't have this mass at the surface that causes the gravitational redshift at the center. It doesn't require double layers. So with a single thin shell, with no additional distributions, you can have the effects of gravitational redshift. And this is, again, I emphasize, this is not true for fluid stars. So for fluid stars, you don't even need a thin shell to produce a shadow, only for gravastars.
Okay, any other questions? If not, then just simply to congratulate you again for the nice presentation.
Thank you very much.
And let everybody know that we will include on the website of the meeting a link to the Wolfram community site where the code is available. Okay, so let's thank again Luis.
Thank you very much.
Okay, so we stop now the morning session and we will continue after the lunch. Thank you, everyone.